Okay, so we are done with that, and then I want to settle on the tutorial. So tutorial, I would suggest to just continue from on Thursday after the lecture, right? So it's basically we continue from 11 to, sorry, that would be 10 to 11, 11. Sorry, that would be 11 to 12, and then continue from 12 to 12:50, right? So this is a lecture, and this is tutorial. So we just continue right after the lecture. How about that? Or do you have actually lectures that are going on at that time?
Okay for me, Doctor.
Okay, Doctor.
Okay, so all right, so we will settle on that, yeah. So the tutorials we will start on week 3. Okay, week 3 we will start tutorial for the first tutorial, and you will get the tutorial questions 1 week before that, right? Which you can actually try. But I'm not very sure about how to get students to participate in the tutorial. Because if you are going to, it looks like it's very hard. I cannot assume that you have any kind of instruments to actually write online. Like here I actually have a Wacom. It's a Wacom stylus. Okay, so that allows me to kind of like write equations on the whiteboard, but I can't assume that you will have that. Okay, so what would be a good way to still get some participation from the students? Because otherwise it may just end up being like you may not actually try the questions and it's just me talking about the solutions. That seems to be a very ineffective, and is ineffective, and also is kind of like boring for me. So do you have any ideas, any suggestions?
Doctor, maybe we can share our screen.
Share the screen, okay, but you would probably have to type out your solutions, right?
Yeah, first, and then we can share it later.
Okay, that's fine. You will type out your solutions, and then you share a screen and you talk about it.
Yeah.
Okay, that's a good idea. Okay, so maybe we try that. However, the students will need to prepare for that. Because otherwise, it will be very inefficient to actually ask students to do that on the spot, right? So that might mean that we have to identify some students who would handle certain questions the week before. So maybe let's see, maybe we can actually have students work in pairs, right? Because we have 39 students. So if you have pairs, we have about 19 pairs lah, about 19 to 20 pairs. And altogether, the total number of tutorial questions for all the tutorials will be maybe slightly more than 20. So everyone will get to talk about it at least once. How do you think?
Sounds good, Doctor.
They work in pairs lah, right?
Yeah.
Then everyone will just have one shot at one question. I think then everyone will have one chance to talk about it, talk about any question.
Yes.
Right, so we try that, okay? So we
Okay.
have a screen share presentation, right? So then we will pre-assign, okay? So work in pairs. Okay. So you have to type out your solution, and are you familiar with LaTeX?
Oh, doctor,
Yes.
maybe we can take picture of our solution and screen share later. Easier. Yeah.
Handwrite, and then okay, you can handwrite and okay, there are many ways to do it. So if you want to handwrite and then scan, right? There's something called cam scanner or something like that. Some apps for scan.
Yeah, because latex is
Yes.
kind of hard to use. I tried using it once, but it's so hard to do the coding.
Oh, do you feel like that?
I had to do some not university course but outside, and I had to do some coding, and I had to learn like the coding for 2 days just to do the assignment.
LaTeX is actually a very powerful text editor. In fact, the notes that you see that I share with you in Spectrum, it's prepared using LaTeX.
Yeah, actually, mathematical a lot of math textbooks or notes, they're made on latex.
Right. But anyway, so I will leave that to you because this is just a tool, and if you feel like you want to use LaTeX, there are many resources to do that. You can actually use. You don't actually have to install anything. You can do that, but it's actually not necessary. There's a site called overleaf.com, which you can just register an account, and you can actually do your LaTeX online. It will save everything online, and then you can generate previews and just download the completed PDF. So for those of you who want to try it, you can try Overleaf. Of course, you can also use Word, but Word is kind of like a bit cumbersome when you need to type out equations and all that. It's actually a very clumsy word processor for when you have a lot of math. But of course, you can also handwrite, okay? And handwrite and scan, okay? So I leave that to you, right? So because the more important thing is the content and not the tool, right? But if you feel like you want to take this opportunity to pick up LaTeX, you can do it, okay? If you have you want to do it in LaTeX, you have something I don't know how to do, you can ask me, right? Okay. So, okay, we're settled with tutorials and all that. Now let me maybe just take you to Spectrum for a while. Let's see, Spectrum is going to open Spectrum. Okay, can you see Spectrum on the shared screen?
Yes.
Okay. So so the announcements, right? Please. So most of the time, most of the announcement will be made in Flock, right? unless sometimes if I announce, like for example, results and things that require more detail, I'll put it in the announcements. Then I'll let you know in Flock that you should read the announcements, right? Otherwise, for short announcements, I don't bother with that because if I put it in Flock, you will read it much faster, and also it's also more visible. Okay, so I'll use it primarily for heavier things, right? Then the attendance record. Let's look at that. So, all right. So every week for when there's a lecture, there you will find that there's such list will come out. Okay. So you can see this. Okay. So you can see your clock in time, and like for example, Bunpo. Is Bunpo here?
Yes, yes.
Okay. Maybe you can try to record this. Yeah. Before 1 o'clock.
Oh, okay, okay. Thanks.
So you do that on your own for the subsequent lectures. Okay, I think everyone else has already signed in. Okay, so that's for attendance. It's settled with that. And then we have the course pro forma, right? So this one is for this course. So you can actually read through this about course learning outcomes, and there are some other boring stuff. Course content, all right? So this is basically some general idea about what's covered in the course, okay? So we do have to use a little bit of abstract mathematics. Sorry. Okay. So we need to use a little bit of real analysis, okay, which we will cover before we actually go into more abstract aspects of probability, right? Don't worry too much about that. We'll try to keep the material simple, right? So, okay. So we have 40% continuous assessment, final exam 60%, but not the kind of way we do the final exam like last sem, right? Because this time the final exam is basically a take home, right? You can actually take home and you'll be given like 1 day to do it, okay? Okay, let's look at maybe this one, course information. All right. So the references, I don't actually expect you to read these references. They are actually quite, if your mathematical preparation is not very strong, they are actually difficult to read, all right? So what I do is basically I get a lot of my materials by picking the parts that I feel are easier to understand from each book. So they are then rewritten in the form of the notes, right? Rearranged in such a way that I feel it's something that you will be able to understand. Okay, so my notes will consist of a mosaic of material taken from multiple sources. Okay, but if you want to read the books, you are welcome to read them. That's so we don't have face-to-face meeting time, so most of the time is not face-to-face, and the rest are your own study times, right? So these are the times: Tuesdays 11 to 12:50, Wednesday Thursday 11 to 11:50, and then we have tutorial from 12 to 12:50. Okay. For continuous assessment, we have 2 assignments, assignment 1 and assignment 2. I'll let you know in advance when the assignment is to be given, right? And don't worry, you will get like usually a couple of days or even 1 week to do the assignment, right? Then your final exam will consist of 2 parts. There's both of them are assignments, take-home assignments are split into 2 parts. One part is 20%, the other part is 40%. Okay. The part that's on 20% will be on week 13, and the one on 40% will be on week 14, right? So week 13 and week 14. So after that, you are done. Yeah, you don't have like last time where you actually have study week and then week 15, 16, things like that. Okay. All right. So these are the topics. This is basically just a rough guide, all right, of the things that are going to be covered in each week. Okay. All right. Okay. So those are the course information. So these are the lecture notes. Right. Okay. Can you see the contents?
Yes.
Okay. So you can read about. There's a prologue. Prologue is basically just some introduction to the notes, right? You can read this on your own. And then you have introduction, all right? So introduction is basically some motivation, right? So I give you some motivation about why we are learning, what probability is actually, and some history about it. Okay, and then after that we have the mathematical preliminaries, which are actually those kind of some real analysis results that are important for subsequent sections. So there's a bit of a lot of technical material over here, right? So we won't be covering this part for today, yeah. Okay, we maybe just slowly go into it maybe on Thursday. Okay. The way to use these notes is that I actually, the way I do it is I put it in a definition, theorem, and then example kind of approach, right? Definition, you need it because you need to, in mathematics, you first have to know what you're talking about, right? So you have to define certain things. And then after that, you have theorems are basically just some results, right? Some mathematical results that may be useful. So, and when it's necessary, the proof will be given. When usually the proof is given when the proof is actually not very hard, or the proof is actually illustrating a useful way of thinking. All right, then I will provide the proof. Sometimes the proof is omitted when actually, if it, especially it's very convoluted, the proof. So sometimes the theorem is simple, but the proof is actually not simple. Okay, so in those cases, we will just make use of the theorem, right? Because sometimes certain theorems, they are just a means to an end, right? They are not an end to themselves. So we will not look at the proof for those cases, right? But only for important ones. Okay, and lots of examples, right? So I believe that your understanding of certain theorems become clearer only when you have enough examples to examine. Okay. So that will be the general layout of this set of notes, yeah? Okay. Okay, so how much time do we have? So it's 12:20 now. So we have about half an hour. Maybe we can actually look at the introduction part. Okay, so what I would like you to do now is to just download this set of notes and spend 10 minutes to read the introduction. Okay, spend 10 minutes to read it, and then we'll come back and have a discussion, right? I think this material should be quite light reading for starters. Okay, so can we do it now?
Yes, doctor.
Okay, so now it's 12:22. So I will resume at 12:32. Yeah.
All right.
Right. Okay, everyone. So we are coming back to the discussion here. Okay. So you have read the introduction, right?
Yes.
Yes.
Okay. So basically, I think all of us have some idea about what probability is, at least from an intuitive point of view. This is very natural, right? I think in the very beginning, people are just concerned. I mean, like people just dealt with very certain things, right? Those are called the laws of nature. Okay, like for example, the two examples there. You take a fish out of water, certain conditions are there, and then there will be certain outcome, right? And the outcome is sure going to happen. All right. So I think in the early days, people observed in nature, and then they came up with certain laws of nature, right? But then, so those describes part of nature, but certain parts of nature, you find that it cannot have any sort of certainty, right? So there's some kind of matter of a degree. So then I give you an example of the surgery, right? You have certain conditions, right? So you perform certain surgery. When that's performed, then you have the outcome, right? Whether the person will live or die. And you find that actually that's not certain, right? If you perform surgery, the person may live or it may die. It's not certain, right? And how should we actually think about such type of a procedure? Do we want to trust this procedure or not, right? So I think most of us would come to the conclusion that maybe if we look at a large number of these kind of instances, right? If we look at maybe 100 cases or even 1,000 cases of such types of operations, then if most of them, the patient survives, then we would have some kind of confidence in the procedure, right? In the condition, right? Rather than let's say if most of the patients die, then we will be afraid to actually take the operation itself. Of course, when you want to, this is what we call empirical way, right? This is a empirical way to approach probability, right? Which means you actually have to do you actually have to do experiments, right? Okay. Like for example, in the operation case, you also have to, when you do experiments, you also have to control, right? Like for example, you have to compare, you have to make sure that the objects that you're talking about are actually similar with respect to other attributes. Like for example, the patients must be maybe around the same age, then they don't have other kinds of illnesses other than the problem that they have. And so on and so forth, right? Because otherwise, these other factors make the object dissimilar, right? So it will be difficult to actually know the effect of the condition, which is the operation on the outcome, right? So this is a very, although we can think about it like this is a very, it's not a very efficient way of approaching the topic of probability, okay? Because you can only make the comment after you do certain things. And sometimes the empirical way of doing things is, it just takes up too much resources and nobody is going to do it, okay? So then that's why people develop the theory of probability. And I think most of us will have some kind of intuition, right, about probability. But intuition alone is actually not enough, and sometimes the intuition can mislead you. Okay, the example that I gave there is the intuition about if you have two events, right? The probability of two events happening together. Let's say these are two events, right? It's actually less than the probability of either one of the events, right? Okay, so intuitively we can appreciate this, right? Because you want two things to happen at the same time, it's actually harder than either one of the things happening by themselves, right? Because you require two things to occur simultaneously. That is definitely feel like it's harder than just asking one of them to be to happen, right? So basically, intuitively, we know it, and then we can express that mathematically as this inequality. And we know that this is true for sure because your A intersect B, right, is actually a subset of A, right? And it's also a subset of B, right? Because the intersection is actually smaller than the set itself, right? So when you apply a probability, right, on this set, this probability is definitely going to be less than the probability of the larger set, okay? So this is at least from theory, all right? But intuitively, we kind of like we are correct even when we don't actually write it down formally. But then the intuition can be wrong in many cases if you don't have a theory to support it, right? So the famous example is the Monty Hall problem. How many of you have heard of this problem before?
I've heard it before.
Monty Hall problem. Anyone else has heard about it, or it's okay not to have heard about it? I just want to have an idea about the exposure to this kind of non-academic.
I never heard about it until now when we read the introduction.
Okay, it's fine. So this is very interesting problem. And it's interesting because of two things. One, it is a very interesting case study of counterintuition, right? The correct answer is actually a counterintuitive. It's very counterintuitive in probability. Most people who were asked this question got it wrong, except a small group of people. And even the interesting part is that a lot of people who got it wrong are actually supposedly people who are highly intuitive in mathematics as well, right? And the example is Paul Erdős. Paul Erdős is if you study number theory before then, you will know who Paul Erdős is. This person has done a lot of work in mathematics. He's a very strong problem solver. All right. Even Paul Erdős got it wrong. Okay. When he heard about this problem, he immediately said out that the answer should be such and such. And then when he was told that he was wrong, he refused to believe it. He refused to accept that he was wrong until finally somebody did a computer simulation of the problem and saw the outcome. Then he accepted that he was wrong. So it's a very interesting case study in how intuition can actually mislead. So what do you think about this? Have you tried to solve it yourself? Okay, if you think about this problem, right? What would if you just look at the problem without any kind of approach, without approaching it kind of like in a more formal way, what answer would you actually give? So maybe I talk about it something like this. So you have the problem is like this. You have 3 doors here, right? You can label the door 1, 2, and 3, right? So suppose there's a car here, right? And the other So the other two doors behind, they are just like goats, right? They're not very good at with the goats, but you have the goatee, right? Okay. So then there's a host here. Okay. So the host can see all these things, but you are the player, right? So you will first make a guess, right? You make a guess and you point to any of them, right? Suppose you point to this door. You guess that this is a car, right? Then what happens is that the host, right? He will always show you a door that has a goat. For example, if you choose 1, right? What he will do is he will either open number 2 and show you the goat, or he can open number 3 and show you the goat. Okay? He will always show you a goat. Then he will ask, do you want to switch? Change your mind. So for example, he will show you 2, and then he will ask you, do you want to change your mind? Okay? And when most people are confronted with this kind of question, right? How would they react? So you choose 1, he will review 2, for example. He will review this. Then he asks you, do you want to switch? Does it matter? Without doing any calculation, if you just use your kind of like intuition, right? What would be the probability of the winning a car if you switch?
%.
So most people, they would think that it doesn't matter. They will say that it is 1/2 because for them it feels like if you show me this thing, right, then I eliminate this. Then the car is either here or here. Doesn't matter, right? You still have 50% chance of being a car. So the majority of people, by a simple argument like this, they felt that this was a reasonable answer. Okay? And actually this turns out to be wrong. But if you just use your intuition just to feel it, it feels right. Okay? Now, so how do we propose to solve this problem? The simplest explanation will go like this. So you have to consider all the possibilities. So this will be a car. So 1, 2, 3. So there are actually 3 possibilities: car, goat, goat. The other scenario will be the car is in here. And this is the last possibility. The car is here. Okay. Now, so then you look at the analysis as such. So in all 3 scenarios, you will pick the first door, yeah? If you pick the first door, right? You will get shown a goat, right? Okay. If you switch, right, do you get a car or you don't get a car? Like in the first case.
Don't get.
You will, if initially you already got the car, right? If you switch, you will get a goat, right? And you will get disappointed. Supposing you don't like goats, okay? But some people like goats more than cars, okay? If you have goats, you can actually breed them, and then you can get more goats. The car, you have to maintain it. So anyway, now in the second case, if you have the second case, you got a goat, right? Okay. The guy will show you, the host has to show you a goat. So he'll show you this, okay? He'll show you this door. And if you switch, right? If you switch, you will get it correct, okay? You get a car. And the third case is the same. You got a goat here. If you choose this, the host will show you this door, right? And if you switch, you will get it right here, okay? So out of 3 cases here, two out of 3, they result in getting a car when you switch. So in fact, the probability of winning a car if switch is actually 2/3, right? It's actually more than 50%. Okay, so this is the argument. You can do a similar analysis. It doesn't matter if you change, if you fix the choice to door 2 or door 3. It doesn't matter. You can actually check. If you fix it to door 2, in this case, if you switch, you will win, right? If you pick this, the host is going to show you this G, and you will switch, you get C. And then here, you will miss it, and here you will get the car. So it's still 2/3, right? Regardless of whether you choose door 1, door 2, or door 3, right? The point is, what's the chance that you win the car if you switch? So it's 2/3. And this example shows you that if you don't actually approach a probability question from the point of view of thinking about its structure, you just go by feelings, intuition. Sometimes you can be wrong, but then you won't feel it. You will feel like you are right. Okay. So this is one of the major reasons why probability has to be approached as a study using some rigorous structure, right? That's why there's these things like things from real analysis, measure theory, they all come in. Okay, is to create that structure so that any statements in probability can be deduced by examining this structure and not by intuition, because your intuition is actually a very weak guide to how probability actually behaves. All right. Okay, so this is just an example of why intuition should not be relied on when we study probability. Okay, because a lot of us will tend to rely on intuition. All right, and then I also gave you some very brief explanation of the history of probability in human civilization, right? So in the old days, people already kind of like use, they kind of like have some fuzzy ideas about what probability is, but because they related it to spiritual things, so they didn't make progress, right? Like the example that I gave you there was concerning in the old days, people would use some kind of mechanism that are actually random, right? In ancient Rome, they would actually kill chickens or goats or something like that. After they kill the goat, they will open up the goats, open up the goat, and then they will check the patterns. How does the pattern of the gut look like? And then based on the pattern of the guts, they will then associate it with some kind of outcome. Like for example, if for example, if they wanted to know whether the harvest for next year would be good or not, right? It's uncertain outcome, right? It may be good, it may not be good. Okay, so then they would actually maybe pick a goat, right? Kill the goat, and then they'll check the intestines, right, for certain patterns. If everything looks normal, if the pattern of intestines just look like normal, they might just proclaim that, oh, then next year the harvest will be good. All right. And if somehow when they check the intestines, they find that there's a tumor, right, some growth and all that, then that might be considered as a bad omen, and they would say that it's bad. But then they would think that they associate the outcome with actually a kind of a chance event, right? Now we understand that, but they didn't realize this at that time. They thought that this was actually a message that's conveyed to them by some spiritual force, okay? And it's the same in ancient China at that time, right? They use something that is, the concept is the same, but they use something different, which is the oracle bones, right? They use the plastron of turtles. You know the plastron of turtles? So you have this is a turtle. So this is a turtle, right? So something like this, right? The shell. So this is a turtle head. The turtle, right? So if you flip the turtle to its underneath, right? So it has a underneath side. So okay. So this piece of shell here is called the plastron. Okay. And what they would do, they would kind of like take this piece and then they will actually bake it over fire. And when you bake it over fire, there might be some cracks. It will crack, right? Maybe crack some patterns like this, whatever. And then they would actually associate these patterns with certain words. All right. These are the early Chinese characters called oracle script. Okay. If you're interested, you can Google and see how they look like. So based on the pattern of the cracks, they were associated with words. And these words may actually, like, for example, mean like if it means war or something like that, then it's a bad omen, right? So they would actually use the bones like that. But then, of course, now we recognize that this is a very strange way of making predictions, because whatever patterns that come out here are basically just random, right? It just depends on how hot your fire is, and then maybe the age of the turtle, right? The strength of the shell, all that. This now we recognize that as random. But at that time, they thought that the message is conveyed by some unseen force, right? So that's the early days. And then after that, you basically have, as humans develop their civilization, then they learn how to gamble, right? So it's through this kind of gambling problems that they found a motivation to actually analyze these games, right? Because there's profit to be made, right? So they became interested in analyzing the gambling games. And this is the point where probability became developed, right? So I gave there the history of two French mathematicians who first solved one particular problem in gambling, called the problem of points, right? So you can read it there. So the problem looked something like that, right? So the first person so the game was interrupted, and then they wanted to see how to split the money in a fair way. So they solved that problem, and from that period on, probability theory became discussed in Europe, and eventually it became most of the things were developed in Europe, right? The ideas of probability, and in fact the theory that you're studying now, it was only formalized in 1933. That was just about around 90 years ago. It's actually, so probability theory is actually considered quite, its abstract foundation is actually considered quite young. okay, relative to other areas like calculus and all that. Okay, but of course it has a very rich history, right? But then during that time, like a couple hundred years ago, when Pascal and Fermat solved that probability problem, they only understood probability in a very limited way. Okay, so now we understand it much better. Okay, so that's a bit about the history. All right, and I hope you like that history. For me, I think it shows how things actually slowly evolve, right? How human thinking actually evolve over time. Okay. All right. So I think that's the we are about time, right? So what time is it now? Okay, it's close to 1 already. Okay. All right. So I think we will stop the lecture now. And thanks for listening.
Thank you, Doctor, for the interesting sharing.
You can ask me anything else about the intro if you want to, right? It's actually a very colorful history.
All right.
Okay, so next on Thursday we will just slowly go into the more abstract material in chapter 3, yeah, of the notes. We won't cover everything, right? Maybe just half of them. Okay, just slowly because we only have 1 hour. Okay, but you can actually have a read first and then to get some ideas. All right.
Okay.
Okay. Thank you, everyone, and see you on Thursday.
All right.
Thank
Thank
you,
you.
Doctor.
Thank you, Doctor.
Okay. Thank you.